Hello, my name is Hans, and I'm a hydrologist with the Arizona Department of Environmental Quality. This presentation provides first-year performance metrics for a remote environmental monitor developed to support field operations in our agency. This presentation was originally shared at the 2017 Annual Symposium for the Arizona Hydrologic Society in Flagstaff, Arizona. This slide summarizes the results of tinkering with open-source hardware for development of a remote environmental monitor. Details about its purpose and design are available in the first presentation shared in the description of this video. Although our bench tests of the hardware proved promising, it had not yet been field tested, so on May 3rd of 2016, we headed out to install our first prototype in a remote ephemeral wash in the upper San Pedro River Basin. This installation took place before the rainy season in southern Arizona, which usually starts in late June, early July. The REM was strapped to a tree adjacent to our sample bottle in the wash, and then wires were run through conduit from the REM to a gypsum block sensor buried next to our sample bottle. As an added bonus, I also installed a cheap rain sensor purchased on eBay in order to monitor atmospheric moisture in the vicinity of the installation. The rain sensor was epoxied to the back of an Altoids box, which made it easier to attach it to a local branch with a zip tie. The enclosure we used was a waterproof kayaker's lunchbox, and its green color was ideal for creating a low-profile installation difficult to see from the channel, thus lowering risk for vandalism or for theft. One of the reasons we went with a gypsum block was to create a low-profile sensor that would be less susceptible to damage during a flood. By burying the sensor next to the bottle, it was protected from gravel or boulders that might be carried in a flood. And here's our gypsum block, buried about 12 inches next to our sample bottle. When significant flow occurs in the wash, we should witness infiltration down to the block, causing it to get wet and change its resistance. The resulting signals are then transmitted to ThinkSpeak, which can be monitored via an internet browser. Once everything was installed, we tested our setup by pouring some water over the buried sensor. We then monitored the response via ThinkSpeak channel married to the REM. The modest amount of water poured on the soil generated a strong response on ThinkSpeak within just a few minutes, which we were able to see on our cell phone screens. During the REM's first 10 days of operation, our first precipitation event was registered by our rain sensor, but our gypsum block reported no moisture at depth in the channel. Our next rains were detected on June 10th, and our gypsum block reported a change in signal 1 day later on June 11th of 2016. Please note that the units on the graph are for a voltage signal, which has been converted to a digital value by the microcontroller. More details on the signals generated by the gypsum and rain sensor are discussed in chapters 4 and 5 of the Arduino training series included with this channel. In response, we hiked out to the site during routine fieldwork on June 22nd of 2016. Sure enough, we found some evidence of flow in a side channel that contributes runoff to the main stem of the wash where our sample bottle and sensor was located. And here we are at the site checking in on the bottle.
Oh, you notice that my brought screws there to replace this one. No go?
No go, huh?
No. So I might get, it looks to me like maybe it just didn't, this little flow didn't come up high enough.
We then tested the sensor by pouring some water on the soil and seeing if we could register a response on ThinkSpeak by monitoring it over our cell phones. Sure enough, we again registered a strong signal. This suggests that although flow likely occurred on June 11th, it was not significant enough to overtop the sample bottle inlet. This resulted in a false positive, and the overall experience suggested I would need to revisit the design of our sensor. We did witness additional rainfall runoff signals from the REM and subsequently returned to the site on August 18th. Sure enough, there was evidence of flow based on the accumulation of channel debris behind the first flush sampler. And upon digging up our bottle, We witnessed a sample ready for collection. Regardless, it was obvious that we needed a more conclusive sensor that would not yield false positives. In response, I came up with this design. Essentially, this is a soil moisture detector that is encased in PVC tubing. Rather than burying this detector, we decided to hang it directly over the bottle. This way, a signal from the sensor would be proof positive that flow overtopped the bottle inlet, thus increasing the likelihood that a sample would be ready for collection. We returned to the site on November 7th of 2016 and dug up the sensor. Although it had recorded multiple stormwater events during the summer monsoon, we were surprised to see that it had reasonable physical integrity, which was surprising given its makeup is essentially no different from drywall. We replaced the gypsum block with our new sensor and tested it by submerging the sensor in a cup of water. The results captured by ThinkSpeak were instantaneous, suggesting it was a good setup. So here's the installation as of November 7th of 2016. Subsequently, flows above the sample bottle were not registered until the summer monsoon of 2017. We were getting conclusive evidence that flows were topping the bottle, but my colleague questioned these smaller spikes. Were these significant? In order to test sensor response, we balanced a cup of water under the sensor and let it evaporate over the course of the next few days. Here you can see the sensor response slowly diminishes as the water level in the cup evaporates. This suggests that even those small responses are proof positive that flow is overtopping the bottle, and thus just as likely significant for determining when a sample has been captured. Given this preliminary success, I investigated how we might simplify our prototype. For starters, I replaced the Arduino and Cellphone hardware with one piece of integrated hardware offered by Adafruit, known as a Feather Fona. By using the Feather form factor, we were also able to integrate this terminal block. This eliminates the need for a breadboard for attaching our sensors while also lowering our overall hardware cost by about $20. We then replaced the Kayaker's lunchbox with a National Electrical Manufacturers Association certified enclosure specifically designed for housing electronics in outdoor environments. And this shows our new design. As you can see, the overall wiring and build is much less intimidating and easier to put together. We also updated the code to work with the Feather Fona hardware and commented it thoroughly so that it could be more easily reviewed, adopted, and modified by others. A link to the code for the original prototype and this improved design is included in the description of this video. Rather than simply working with changes in state for detecting on-off conditions, we also purchased an ultrasonic sensor in order to send quantitative rather than qualitative data to ThinkSpeak. This particular sensor is useful for determining the stage of a stock tank. Additional sensors were purchased for measuring atmospheric temperature and humidity and successfully tested. Our upgraded box was then installed at a stock tank that regularly fills up during the summer monsoon. Thanks to support from the Agricultural Research Service, we attached the REM to infrastructure already in place for measuring stage in the tank. The goal of the installation was to see how our system would perform in comparison to more formal hardware managed by ARS. Unfortunately, the high banks of the stock tank blocked the REM's visibility to local cell phone towers. As such, it quickly became apparent that we needed to develop a solution for monitoring remote sites where cellular service is limited. In response, I started investigating satellite telemetry and came across a satellite modem known as RockBlock that communicates with the Iridium satellite network. These modems are used for tracking shipping vessels in the middle of the ocean where no cellular telemetry is available. More importantly for our application, these modems are capable of interfacing with Arduino through an Iridium SBD library, which greatly simplifies their use and programming. Finally, although the cost of the satellite modem is significantly higher than cellular, costs for transmitting small packets of environmental field data are very reasonable. In addition, the vendor provided us with excellent customer service in meeting a request that their servers used to receive data from the RockBlock modems be upgraded so that they could interface with ThinkSpeak. On April 21st of 2017, we managed our first successful post to ThinkSpeak from a RockBlock modem interfaced with an Arduino and transmitting from a location close to the Los Angeles International Airport in California. In response, we built our new satellite-capable REM integrated with the weather-resistant MaxStor ultrasonic sensor for measuring stage in a stock tank and an AM2315 encased temperature humidity sensor. Our bench tests of the ultrasonic sensor were successful. However, to realize accurate temperature data, we observed the need to shield the temperature humidity sensor to avoid bias from direct sunlight on the sensor. We did this by placing the sensor in a PVC pipe. And so on July 3rd of 2017, our colleagues from the Agricultural Research Service helped me install our new satellite telemetry capable REM at the stock tank in the upper San Pedro River Basin. Upon installation, the ultrasonic sensor reported bad data, but the temperature humidity sensor were working as planned. I suspect there's some electrical interference impacting the performance of the ultrasonic sensor, and I'm currently debugging the same. Rather than bring the unit back to the lab, we left the installation in place in order to evaluate its performance in posting temperature and humidity data to ThingSpeak. In the next few slides, I'll summarize telemetry metrics associated with both our cellular-based REMs and the RockBlock Iridium REM for what we've managed to test to date. Let's start with the performance of our first prototype, a 2G cellular-enabled REM running on the T-Mobile network offered by a reseller known as Ting. With respect to telemetry, the REM posted data consistently between May 3rd, 2016 and February 12th of 2017 with no need for maintenance, a period of over 9 months. Around February 12th, we started noticing abnormal periods of drop data, which we attributed to a failing battery. For this period, the modem was programmed to post data to ThingSpeak once every 10 minutes. Accounting for the need for the post algorithm to execute, the actual time for each post is actually closer to 12 minutes. Accounting for drop data, the frequency was closer to one post every 12.5 minutes. The max downtime was 59 minutes, which we attributed to poor cellular coverage in the area where the REM was installed. This accounted for less than 1% of the time that the REM was in service. On May 7th of 2017, we revisited the site and gave the system a tune-up. One important change I made was to lower the capacity of the LiPo battery from 2,000 mAh to 500 mAh in order to see if we could lower cost of production for multiple deployments. After the tune-up, the system performed well through August 16th of 2017. On that day, the system went offline abruptly. We haven't been to the site since, so it's not clear if the REM was damaged by vandals, environmental conditions, or if the lower capacity battery we installed resulted in a shorter period of performance. So here are the performance metrics for the REM post-tune-up on May 7th of 2017. Again, the system performed well while online, and we haven't yet definitively determined the reason why the REM failed post-August 2017. One thing I did notice in the battery charge-discharge profile is a series of peaks and valleys over a 24-hour period, which is something I didn't see when the system was running off a higher capacity battery. I suspect the increase in the number of charge-discharge cycles may have shortened the life of the battery hosted by the system, since LiPos are affected by the same. As such, I'd recommend using a higher capacity battery like our original 2000 mAh LiPo. With respect to our improved 2G cellular REM, we have successfully bench tested the hardware and code with an ultrasonic sensor, but have not yet field tested this system. We do expect improved performance relative to the first prototype, since the configuration is simpler and the supporting sketch has been significantly improved. We have also successfully bench tested a Feather Fona 3G, which runs on the 3G network. This system works well for texting data to cell phones, but we've been unsuccessful in posting data to ThingSpeak with the 3G libraries provided by Adafruit for this particular hardware. Further details are available in the thread shown on this slide. Finally, this summarizes the successful telemetry realized by our satellite REM tested between July 3rd and August 7th of 2017. Because of the higher cost associated with posting data using satellite telemetry, we employed a longer time lag between data posts. Instead of setting a time lag of 10 minutes, we set it for 2 hours. For this hardware, we did realize some data gaps with downtimes of up to 22.4 hours. After communicating with the vendor, we determined that the cause of the drop data was lack of error handling in the code that I had developed. Error handling is needed in the event that transmissions from the modem are not completed before satellites drop behind the horizon. We're updating our code to handle these errors when they occur. Once that code is updated, documentation and programming for this upgrade will also be posted. With respect to Year 1 tests, this table summarizes my results through August of 2017. Our best performer was our first prototype consisting of an Adafruit Fona 2G Breakout running in tandem with an Adafruit Pro Trinket, which is a variant of an Arduino. As you can see here, field tests were good and the cost is very reasonable for both hardware and 2G cellular service. For areas where cell phone service is not available, the Iridium satellite network accessible through the RockBlock modem is a little more expensive, but shows great promise pending upgrades to our code. In all cases, data costs can be improved by being a little more strategic with data collection, perhaps by transmitting only when there is a change in state rather than at a fixed frequency. My conclusions are as follows. With respect to cellular-enabled environmental monitors, we can now build low-cost cellular REMs on the Arduino Fona platform running on the 2G network that provide us with real-time stormwater conditions through the Internet of Things on platforms like ThingSpeak. We can also text environmental data to a cell phone on Arduino Fona platforms, but we are not yet at the point where we can use 3G with the Internet of Things. And additional homebrew and/or inexpensive environmental sensors are relatively simple to integrate into the Arduino Fona cellular REMs. With respect to satellite telemetry, we can now integrate satellite networks into our REMs at relatively low cost, but we must be more strategic in data collection given higher data transmission costs. RockBlock now works with ThingSpeak, and our pilot telemetry tests and the vendor have pointed us to the need to improve our coding. In regards to the open source Creative Commons approach to remote environmental monitoring, commercial package alternatives are considerably more expensive, but good customer service is priceless. And sustainability and adoption requires additional documentation, outreach, and cross-pollination of ideas. I'm in the process of documenting additional details for the REMs discussed in this presentation, which will be shared shortly. Not being an electrical engineer or programmer, I did have to do some research on these platforms, so I know what it's like trying to take on a topic like this from scratch. If you're new to Arduino and also interested in designing your own hardware, I've developed a suite of training videos that go over the very basics of DC circuits and how to use an Arduino to monitor and react to environmental variables. These were originally developed for ADEQ staff here in Arizona and improved based on input from colleagues at a local makerspace here in Tucson, Arizona. In order to make these universally accessible to the public, the series is posted to my personal YouTube channel, accessible via the noted link. This concludes ADEQ's first year summary of our exploration into open source alternatives for remote environmental monitoring. Since most of this work is done outside of working hours, it's approached as time allows, but we are making progress and will continue experimenting and improving over the coming months. Thanks for watching and stay tuned for updates including instructions on how to build an REM of your own.